go to the previous lecture. And in the end, we formulated a lemma, which says that for any homomorphism, the inverse image of a subspace in the range is a subspace of the domain. In particular, the inverse image of the trivial subspace of the range is a subspace of the domain. So in other words, so if we consider this is vector space V, this is vector space W, and we are considering homomorphism from V to W. And so if we apply homomorphism to the whole vector space V, we probably will get not necessarily complete, but some part of vector space W. So, and this is nothing else, but sometimes denoted by these or range of the homomorphism. So it's all this thing. So now the statement is the following. The only thing which we know that if we take 0 vector, right? We know that 0 vector by the homomorphism will be mapped into the corresponding 0 vector here. Now, if I choose the subspace, some subspace in the subspace inside of my range, right? So subspace S. Okay, then first of all, we know that all subspaces contain a 0 vector, so it will contain a 0 vector. Now, statement of the theorem says that it doesn't matter what will be this subspace S, but if I will find, so you see, S is a subspace of the range. So it's not necessarily the whole range. It can be some subset of the range, right? So if I will find all possible vectors from my domain, this is codomain. So if I will find all possible vectors from my domain, it says this thing is called inverse image of S. So all possible vectors from the vector space V, which end up in the subspace of the range, right? So then the statement is that this is also subspace. Yeah, so S was a subspace of the range. And then the inverse of this is also subspace. And in particular, we know that 0 vector is mapped to the 0 vector. But if I will consider all possible vectors which are mapped into the 0 vector, so then this is also a subspace, right? Because 0 vector here is the trivial subspace, right? So, and this is inverse image of the trivial subspace. So which means subspace containing only 0 element. Okay, the proof is the following. So let H, so if I have this homomorphism, and S is a subspace, as I just explained. So let us consider inverse image of S. So inverse image of S, meaning all possible vectors. So all possible vectors which are which map into this subspace S. So first of all, it's non-empty because contains 0 element, right? Because we know that every subspace contains a 0 element, so there is a 0 here, and we know that 0 element maps into the 0 element by the homomorphism. So it means that 0 element belongs to this inverse image, right? So it's non-empty, which is already good. So now to finish, we need to show that it's closed. We need to show that that H inverse of S is inverse image of S is closed under linear combination. So how to do this? We will do this in the following way. Let V1 and V2 belong to this inverse image. What does it mean? It means that HV1 and HV2, they belong to S, right? To belong to this subspace, this one. So then, if we consider CV1 plus CV2, C1 V1, C2 V2, then if we will apply our homomorphism by the property of preservation of structure, we have this, but this belongs to S, right? So because subspace is closed with respect to the linear combination, right? So, but if it belongs to S, so it's some vector in the subspace of the range, then because we said that this is inverse image of the subspace, meaning all possible vectors which are mapped into this subspace of the range. So it means that this thing belongs to the inverse of S. So I started from two arbitrary vectors belonging to the inverse image, and I got that their linear combination also belongs to the inverse image. So that's it. So I have a closure, right? So I have shown that there is a closure with respect to the linear combination of the vectors. Okay, now we already had it. So I said,
Professor, can we kind of go over that for a sec? So I understand how it's closed under linear combinations, but how does that like go to prove that it's a part of the inverse of S?
Okay, so have a look. I have chosen V1 right here. Okay, let me use different color. Yeah, let's say I choose V1 here, and let's say V2 here, right? Okay.
Okay.
So I know that they are mapped somewhere HV1 and HV2 inside of my subspace of the range S, right?
Yes.
Why? Because here I have all possible vectors which are mapped to the S, right? To the subspace S, right? Okay. So after that, I'm saying that let me consider linear combination of these two vectors. Linear combination of these two vectors, if I apply homomorphism, also belongs to the subspace S, just from the linearity, right? So because this is an element of the subspace, and this is element of, I mean, this is, and these are elements of the subspace S. But we know that subspace is closed with respect to the linear combination, right?
Yes.
So it means that their linear combination, this one, also belongs to the subspace S, right? But we said that inverse image, this one, contains all elements which are mapped to the subspace S, right? So it means that I have shown that this linear combination also belongs to the inverse image, right? Okay, probably it's better to write it not like that, but like that. That this thing belongs to the inverse image.
Okay. Yes, thank you. That makes a little bit more sense.
Okay, a little bit.
Well, it definitely makes more sense now. I understand where that comes from. It's still an abstract concept, just a little bit.
Yeah, it's okay. So now let me give a definition of the null space. The null space, or kernel, of a linear map H, which is mapping vector space V into vector space W, is the inverse image of the zero vector in the double. So, and we have shown that, so it's this green subspace here. So we have shown that the null space is a subspace of the domain because here, I mean, zero vector is a trivial subspace, right? So we have shown that inverse image of any subspace is a subspace, right? So it means that we know that this is a subspace. So in other words, N of H, null space of H, is the inverse image of the zero vector, or in other words, all vectors in the vector space V such that they are mapped to the zero vector by our homomorphism. And the dimension of the null space is the maps of homomorphisms nullity. Okay, in other words, if we have V and we have W, so we know that for sure zero vector of V is mapped to the zero vector of W. We have proven that. But also it could be some subspace, some set of elements which is mapped to this zero vector. So a simple example is the following. So for example, let me consider d2 by dx squared applied to the space of polynomials of degree 2. So I know that, okay, you can say that you will map it onto the same vector space, right? Okay, let us consider, so what it is. So if I will apply d2 by dx squared to that, so what I will get? I will get 2a2, that's it, right? So first derivative will kill this constant, right? And decrease the power here. Second derivative will kill this term, which will be constant term already, and decrease the power here, right? Is it clear? Is it clear or not?
Clear.
Okay, so as a result, could you tell me what will be the null space of second derivative of the homomorphism, which is corresponding a second derivative? Okay, have a look here. So I got 2a2 as a result, right? So it means that I can choose any, literally any. So if I want to get this to the zero vector, right? So I need to have this to be zero, right? That's it. These
So
are
would
the
it,
only.
so would it be all polynomials of a1x plus a naught?
Right? So polynomials of degree 1, which is a subspace of polynomials of degree 2, right? So all of them, they form the null space. So P1 is a null space of d by dx squared. Right? Is it clear or not? Any questions? Okay, another example. Let us consider the following map. So in other words, we consider homomorphism from R2 to R3, right? Is it clear or not? Any questions? Okay, so in order to find a null space, I need to have this to be a zero vector, right? So, okay, then I'm getting condition this, right? Right or not? Is it clear?
Yes.
Okay, wonderful. So from here, I know that if I want to have to get a zero vector here, the only vector which will give me in R2, the only vector which will give me this result is which one?
0, 0.
Just the zero vector and not two, right? Okay, now let me change it a little bit. Let me, for example, write something like that. So what will change? Here I will have this, right? So it means that if x is equal to y, right? I will get as no, it will still the same. Okay. Something like that. Yeah, this is better. So then I know that if x is equal to y, so I will get a zero vector, right? So in other words, all vectors of the form xx form the null space, right? Clear or not?
Professor, is it also possible to say it's YY?
Yes, sure.
Okay.
So you could really write here AA. A is any real number, right? So any vector which has two-dimensional vector, which has, I mean, two-dimensional column vector, which has first and second entry equal to each other, will form them, will belong to the null space, right? Is it clear or not?
Yep.
Professor, what's the nullity of that null space?
Of this null space?
Yeah.
So have a look. You can write it like that. It means that the null space is spanned by how many vectors?
Infinite?
No.
One, I guess.
Span.
One.
So the nullity is a span of the vector 1, 1.
Okay.
Right? So it means that you have one vector in the basis, dimension is 1, right?
Okay.
Here, could you tell me what will be the nullity?
One.
What is the dimension of the zero subspace?
1.
0. So it's a special case. It's a special case as a trivial subspace has a dimension of 0. Always. So,
Professor?
Yeah, go ahead. Here, for example, let us talk about this. What is the dimension of the nullity in this case?
Should be 2.
Right?
Because the basis is x and 1, right?
Exactly. I mean, for example, x and 1, right? So you know that natural basis is convenient, but it's not necessarily the best basis to use, right?
So is that a1x plus 8? That's our null space because we had to set a2 equal to 0. That's all we're left with in the original, right?
Yes. Yes. The only requirement for the vector to be mapped to the 0 vector, right, is this. A0 is equal to 0, right? A2,
So
sorry, A2 is equal to 0, sorry.
Rest of it then is our null space, our map.
I mean, there are no conditions on A1 and A0. No conditions. Means that they can be any. It means that any polynomial like that is mapped to the null space, right? So as a result, I know that my null space is space of polynomials of degree 1, which is subspace of the polynomials of degree 2, right? Any questions?
Yeah, I kind of wanted to expand on a question that Michael, I think it was, had. And he had said, what's the null space of the null space?
No, not null space, nullity, you mean?
Oh, okay.
No,
I must
he
have
asked,
heard that
what is
wrong.
nullity? Nullity is the dimension of the null space.
Okay. Then
Yeah.
I must have misheard it wrong. Thank you.
Yeah, because null space is defined for the linear map for homomorphism. So it's a property of homomorphism. Have a look. Null space of a linear map, you see? Because you need to know, you need to have a map in order to define the null space. Okay, great. Now I will prove extremely important theorem. It's called Rank-Nullity Theorem. By the way, some of you used, if you remember, so I essentially, when I was asking you to find the dimension of the solution of the homogeneous equation, right? So what is homogeneous equation? So coefficients matrix applied to the x1, xn equals the null vector, right? So you can easily show that this is a linear transformation, preserved structure. And then I was asking you to find the dimension of the space of solutions of the homogeneous equation. But space of solutions of the homogeneous equation is nothing else but the nullity, or not nullity, null space of this linear transformation. So when I asked you to find the dimensional space of solution, I was asking you to find the nullity of this linear transformation. Now, and also, if you remember, in the part in the problem 5 of the midterm, I asked you also to find the rank of the corresponding coefficient matrix. So now you will see some of you already used that. Really, you used this, and I was not considering it as cheating. So if you know this, it's good. So, but still, only now we are proving this theorem. A linear map maps rank plus its nullity, equals the dimension of its domain. So in other words, for this particular case, because for this system of linear equations, as I said, so it's possible to show relatively easy. It's possible to show that it's a linear transformation or linear map. So rank plus nullity equals to dimension of its domain. In this case, it's n, right? Because it's defined for every vector, column vector belonging to Rn, right? So statement is that rank plus nullity. So in other words, number of linearly independent vectors or columns in the coefficients matrix plus dimension of the space of solutions of the homogeneous equation is equal to n. Okay, but we are proving it not only for systems of linear equations, which is just special case, as we shall see, very general but special case of a linear map. So we will prove it for a general linear map. So, okay, once again, we consider homomorphism or linear map from vector space V to vector space W. And let Bn, which is beta 1, beta k, be a basis for the null space. Okay, let us expand basis for the null space to basis of the entire domain V. So in other words, may have this, which consists of basis of the null space plus some more vectors. We can do this. We discussed that, and we have proven. We had a corollary about that. So process is the following: you take the basis of the null space, right? So and then let us suppose that null space do not coincide with the whole vector space V, right? In such a case, what is the situation? The situation is that there will be vectors in V which are not spanned by the corresponding vectors of the basis of the null space. So take any vector like that, which is not spanned, doesn't belong to the null space, essentially. So then this vector cannot be linearly dependent on the vectors of the null space, right? So you added one vector to the basis. You have now k plus 1 linearly independent vectors. Okay, take any vector which is not spanned by this basis. If this basis is spanning the whole vector space V, then we are done. If it's not spanning the whole vector space V, take any vector which is not spanned by these k plus 1 vectors. So it's linearly independent with the previous ones, right? And so on. So and you can continue like that until you will get n linearly independent vectors for n-dimensional space V. So and then you know that in n-dimensional space you found n linearly independent vectors. Then by the theorem which we have proven before, we form a basis, right? Okay, essentially what we need to do. So now we need to prove that H B K plus 1 N is a basis for the range space. So remember that rank of H of some homomorphism is the dimension of the range of the homomorphism. So by definition. Okay, wonderful. So then counting these k vectors, they form the basis for the null space, right? So nullity of H is equal to k, right? So if we will prove that these vectors, they form a basis for the range, then we know that sum of the nullity and dimension of the range space, which is a rank, is exactly equal to the dimension of the domain of the original vector space. Okay, so how to do this? Let us consider, first let us show that these vectors are linearly independent. I mean, these vectors. So how can we do this? Let us, so standard situation. So what we do, we just take these vectors and consider their linear combination, right? Oops. K plus 1. Yeah. Now everything is good. So we consider their linear combination because, and if we will be able to show that all these C's are equal to 0, then we know that these vectors are linearly independent. Okay. Now let us use linearity of our transformation H. We can write it as H CK plus 1 H. Oops. Beta K plus 1 Cn beta n. Right? So we used linearity. But this vector, you see, it's mapped to the 0 vector in the vector space W. It means that this vector belongs to the null space of my homomorphism, right? So it means that the vector, this vector, can be represented, because it belongs to the null space, as a linear combination of vectors of the basis of the null space, which is this, right? because this vector belongs to the null space. So, and beta 1, beta k, have a look, they form a basis for the null space. So then, obviously, this has to be true. Okay, how can I write it? How else can I write it? I can write it as C1 beta 1 plus and so on plus CK beta k plus or minus, doesn't matter really. Or, yeah, just like that. And all these is equal to the 0 vector, right? I essentially subtracted left-hand side from the right-hand side. Okay, but this is nothing else but linear combination of vectors of the basis of the vector space V, right? From here, I know that C1 equals to C2 equals to CK, CK plus 1, they all have to be zeros. So we have proven that this is true, and it means that these vectors are linearly independent. Is it clear or not how I've done this?
It's clear, I think.
Okay, wonderful. Okay, yeah, by the way, I will call this basis of the range. Okay, wonderful. Now, I have shown that these vectors are linearly independent. Now I need to show that they span the range, right? So that these vectors span the range. So let us consider h of v, which belongs to the range of our homomorphism, right? Okay, now, first I can express this vector v, right? As a linear combination, C1, C1, and so on till Cn beta n, right? So beta 1 and till beta n are vectors of the basis, vectors of the basis for V, right? Okay. Now, if I will apply this, what I will get? I will get this, right? Now I can use, so I will do the following. I will leave this as is, and so I will have this like that. And I will use linearity for everything else. But pay attention, what is that? Vectors from beta 1 to beta k they form a basis for the null space. So then this belongs to the null space of H. So could you tell me what these will be equal to?
The 0 vector?
Sure. It's a 0 vector in the space W, right? So it means that I started from the arbitrary vector, right? In the range, and any vector in the range can be represented as linear combination of these vectors, right? So, but before I have shown that these vectors are linearly independent. So from here follows span, and altogether it follows that span plus linear independence BR is a basis for the range. Clear or not?
What are you labeling BR as?
Here it is. Okay, let me use this. Is it clear? So have a look. Have a look. We started from. So I said that let us suppose that these vectors form a basis for the null space, right? Just k vectors, right? Vectors from beta 1 till beta k, right? Then I said, okay, now I will extend this set of vectors which form a basis for the null space. So if we are making not to only to 0, right? So then there will be vectors which are not mapped to 0, right? So as a result, it means that I can extend this basis to form the basis for the whole original vector space, the whole domain, right? So then what is the dimension of the whole domain? Is n, right? Dimension is n. So now what I'm trying to do, I'm trying to prove that this basis BR is a basis for the range. And then, obviously, what is the number of bases in BR is n minus k, right? Right? N minus k. So if I will add this number of vectors, which is equal to this number of vectors, to the number of vectors corresponding to the dimension of the null space, which is nullity, I'm trying to prove that it will be equal to the dimension of the original vector space or the domain. So that's it. Okay, is it more clear now or not exactly? If not exactly, please ask.
It's clear how you get into the rank and to how it's showing it's linearly independent. I guess I'm just not seeing that last part that you said about how the rank and the nullity is equal to the dimension.
Okay, so
I understand everything else, and I can see how
okay.
that's true.
Yeah. Okay. What is the nullity?
It's just k vectors, k number of vectors.
K equals the nullity, right?
Mm-hmm.
By definition, what is the rank of the homomorphism? It's the number or dimension of the range. right?
Okay.
So rank is equal to dimension of the range of the homomorphism, right?
Yes. Okay.
So if you know how to show that this is these vectors, they form a basis for the range, right? So then number of vectors here is exactly the dimension of the range, right?
Okay. Now I get it.
So this nullity plus dimension of the range gives you the total number of vectors in this basis, right? In the basis BV. Okay, perfect. So once again, have a look. If we have a coefficients matrix, right? And we have an applied this coefficient matrix to the, or consider just coefficient matrix or system of linear equations with n unknowns. And we have homogeneous system, right? So what is the dimension of the space of solutions of the homogeneous system? How it's connected with the number of free variables? Okay, your solution will be this plus again free variable and so on, right? So essentially nullity or the dimension of the solution space of solutions of the system of homogeneous equations or dimension of the null space, right? In this case, is equal to number of free variables, right? Right or not? I want this to be clear. So you see, if I hear silence, it means that it's clear to everybody, right? So
Can I just clarify something real quick?
sure, go ahead.
So the free variables would be like x1 equals like alpha1 x3 plus alpha2 x4.
Yeah.
That
Let me write some specific case, right? So if I will bring it to the reduced row echelon form, right? So I will have it like that, right? Right?
Yes.
Right on. Okay. So as a result, I'm getting these, right? And my solution is nothing else but what? It will be, okay, sorry. It will be x3 multiplied by, because x3 is equal to x3, right? So it's 0 minus 2, 1, 0, right? Right or not?
Yes, I see that.
Yeah. So, and if, for example, I would have not x4 here, but let's say x5, right? And I would have something like that, right? So what would it mean? It means that for x4, I would have plus 3x5 equals to 0, right? And x5 equals to x5, right? So no any, yeah, like that. Then I would have like that 0, okay, x5, 0, 0, 0, minus 3, 1, right?
Okay, so then that means that the nullity for that one would be 2.
Exactly, because these vectors, they inevitably will be linearly independent. Why? Because you will have 1 at the position corresponding to this index, right? But here you inevitably will have 0, right? And 1 to the position corresponding to this index, right? So they always will be zeros and ones in the corresponding positions corresponding to the free variables, right? So they cannot be linearly dependent as a result, right? Because from this 1, you cannot make this 0, and from this 0, you cannot make this 1, right?
Yes, that's true.
Yeah, so vectors correspond, these vectors will be linearly independent, right? And definitely these vectors span the solution of the homogeneous system of linear equation, right? Which is a null space, right?
Yes.
Yes, so nullity in this particular case is 2, right? Now, could you tell me what is the rank of this matrix?
The rank of this matrix is going to be the range.
No. For this matrix, just for this matrix, just forget about the range of the homomorphism. Just for this matrix, rank is the number of linearly independent columns or rows, right? So what is the number of linearly independent columns in this case?
3.
Right? Number of leading ones, right?
Yeah.
Or number of leading variables, right? So have a look from here, because we know that under elementary row operations, a relation between rows stays the same, right?
Mm-hmm.
So from here, I can see that, for example, the third column can be, how can you express the third column through other columns?
The third column through other columns?
Yeah, you see, leading ones, right? They form a natural basis for the columns of this matrix, right? Because they have 1 and zeros everywhere else, right? So, for example, U3 is nothing else but 2 U2, right? So this column is nothing else but 2 these columns, right?
Oh, okay. I see what you mean by that.
And what about U5?
It's just equal to 3U4.
Right, 3U4. Perfect. Now, what is good about that? Because I know that elementary row operations do not change relations between columns, then for a regional matrix A, right, I will have exactly the same. I know that A3, the third column will be 2, A2. And A5 will be nothing else but 3, A4, right? Because relations do not change under elementary row operations between columns, right?
Oh, yes.
Now, have a look. This is what will happen if I will consider these column vectors, right? So what does it mean? So how can I write it? I can write it as A1 x1 plus x2 A2 plus x3 A3 plus x4 A4 plus x5 A5 equals to 0 vector, right? Now, what else can I do? I can do the following. I can use these relations to exclude columns which correspond to free variables. So, and I'm getting right?
So you're just using the fact that since the column 5 is equal to 3 column 4, and the fact that column 3 is equal to 2 column 2,
I can get rid of them. I don't need them, right?
But you use that idea like in the matrix, like A3 is equal to 2A2, A5 is equal to 3A4.
Yeah. Here, when I wrote A1, so I mean that this is a column vector A1, right? This is column vector A2, column vector A3, column vector A4, column vector A5, right?
Okay.
So now what I've got that the result of application of this system of linear equations, right? Or you can say result of application of this coefficients matrix to this vector of unknowns, right? Is this, right? So I know that my range is spanned by these linearly independent vectors. Their linear independence I know from the linear independence of this U1, U2, U3 here, right? Because these are linearly independent, right? They obviously, because they have zeros everywhere else but in the leading ones, right?
Yes.
So they are obviously linearly independent. Because relations between columns stays the same, it means that original A1, A2, and A4, exactly like here, they were also linearly independent, right? And others are linearly dependent. So, and now here I'm showing that my range is spanned by linearly independent columns. So span and linear independence means that these columns form a basis for the range, right? So as a result, could you tell me what is the range? What is the dimension of the range? Is exactly the number of leading ones here, right?
Yes.
Have a look now. Number of leading ones plus number of free variables gives you what?
The dimension?
Number of these x's, number of unknowns, right? But what is that? This is nothing else but domain, right? Your domain is Rn, right? In this case, R5, right?
Okay, so I feel like that's the part that I got
uh,
confused. So the number of leading variables is the rank, but it's also just the dimension. But if we're talking about the dimension of the domain, then it's the rank plus the nullity.
plus the nullity, right? Because it's inevitably for the system of linear equations, number of leading ones plus number of free variables gives you exactly the number of unknowns. And number of unknowns is nothing else but the dimension of the domain or the original vector space, which is Rn.
Oh, okay. So, okay, I understand that statement better. Thank you for.
Yeah, you see, this is extremely important example of application of this theorem. This theorem is true for any, this rank-nullity theorem is true for any homomorphism. So in just a few, probably even on this lecture, I will show that every homomorphism can be represented as multiplication of some matrix on some column vector. So every, and vice versa, every matrix corresponds to some homomorphism. And as a result, we can apply here the rank-nullity theorem. And from here, you can see that the nullity plus, dimension of the null space plus dimension of the rank equals to the number of unknowns for the system, or you can say number of columns of the matrix, of the coefficients matrix, if you like, which is the same, right? So this is extremely important application of rank-nullity theorem to specific case of the linear map. Okay. Now,
I have a question.
Go ahead.
Is that similar to saying that the basis of the original vector space equals the basis of the range plus the basis of the null space?
You see, it's not exactly, because basis range can have a different dimension, right? If null space is a subspace of the original vector space, right? Have a look here. Sorry. Yeah, like that. So I don't want to repeat this wonderful performance which I did once. Okay, so have a look. This is this is the basis of the range, right? Because null space, these are all possible vectors of your original vector space, which are mapped to the zero vector, right?
Right.
So null space belongs to your original vector space. This is why they can share the vectors of the basis. But the range is the result of application. So you see here, you see, we have this. Yeah. You see, we have this H here. So basis of the range is, these are different vectors. They have different dimension. So like here, for example, pay attention that what is the, so you see, null space is mapped, is spanned by vectors containing how many entries? Five entries, right? So null space is spanned by 5-dimensional column vectors, right? And vector of the null space is 5-dimensional column vector, right? But the range is spanned by the column vectors, linearly independent column vectors of the original matrix. But they have how many entries?
3.
3, right? So you see, range is 3-dimensional. I mean, no, not 3-dimensional. Range is a subspace of 3-dimensional vectors or 3-dimensional column vectors, right? Is a subspace of 3-dimensional column vectors, while the null space is subspace of 5-dimensional column vectors. So what I'm trying to say that these are two different vector spaces. As a result, the basis for the range, if null space is a part of the original vector space, subspace, this is why it shares, have a look. This is basis for the null space. This is basis for the null space. It partly covers the basis for the original vector space. While basis of the range, this one, contains h applied to the basis of the original vector space. So it's different entity. So it's different object. I mean, theoretically, at least in principle. Is it clear or not?
That makes sense.
Yeah. So it's not exactly like that. So you can find, and I have shown here, you can find the basis of the original vector space such that part of it will be vectors of the null space, and the basis for the range will be this linear map applied to the rest of the vectors of the basis of the original vector space. Is it clear?
Yes.
Okay, perfect. So unfortunately, the time is up. So, but I hope that at least you were okay. Let me please let me formulate a corollary so that I don't need to come back. Corollary of rank-nullity theorem. The rank of a linear map is less than or equal to the dimension of the domain. Equality holds if and only if nullity of the map is 0. So what does it mean that nullity of the map is 0? It means that only 0 vector from the original domain is mapped to the 0 vector of the codomain or the resulting vector space. So only in such a case, the rank is equal to the dimension of the domain, which means that we have what? Isomorphism, right? Only for the isomorphism we have such situation, right? Okay, thank you very much.